Topic 7b, numerical analysis of slab waveguides. As far as the computation goes, there really won't be anything new in this lecture. This is an exercise to show how our one-dimensional finite difference analysis can be used to solve a real-world problem. And in this case, we'll be calculating the electromagnetic modes that exist in a slab waveguide. I have no expectation that anybody listening to this lecture has an in-depth knowledge of electromagnetics. This is a computational course. However, if you're solving a problem in physics or science, it's inherently tied to the theory of whatever it is you're solving. So I will step you through the electromagnetics, and I'll show you how to go from the equations describing electromagnetics to that final equation that we will solve using our finite difference approach. So we'll talk about slab waveguides. After that, we will enter the finite difference method proper. And for computational algorithms like this, I like to break it down into 3 steps: formulation, implementation, and then practicing it. So in the slab waveguide section of this, we will be deriving the fundamental equation that we have to solve. When we get to formulation, we will then put that into matrix form to solve. We will discuss the implementation, and then we'll give you an example to benchmark your code off of, and at that point, you'll be ready to analyze any slab waveguide. We begin our discussion with a material parameter called refractive index. And it turns out when a wave goes from one material to another, it either speeds up or slows down. And we can characterize the speed of a wave inside of a medium through this parameter called refractive index. The refractive index is the factor by which a wave slows down relative to a wave in outer space, or sometimes we just call it free space. So if refractive index is 2, the wave is traveling at half the speed that a wave would in outer space. So we're going to understand our waveguides through this parameter refractive index. It's interesting to note and useful that the frequency of a wave is the constant concept. That's the most fundamental thing. That does not change from one medium to another, assuming we have linear materials. There are cases where that can change. But the wavelength does change as the wave speeds up or slows down, and that can be confusing. So the wavelength changes depending what material you're in. The frequency is the constant thing, and that's just a consequence of the speed of the wave slowing down or speeding up. It turns out the refractive index, or the change in the speed of a wave, is what's responsible for a wave bending at an interface. If you've ever stuck a stick in water or put your spoon in a glass of water or looked at it from the side, it appears to bend. And that's a phenomenon called refraction, and it's quantified by an equation called Snell's law, which we're showing here. And the angle of a wave coming in and hitting an interface is a different angle than on the other side, and of course related through this equation, Snell's law. So if we look at this configuration, we see that on the low refractive index side, so in this case that'll be the side of N1, the angle theta1 is larger than it is on the other side. That's very indicative of the case where the refractive index is lower on the side with a larger angle. Now let's think about a special case. Maybe this is a little bit impossible, but imagine your angle of incidence was 90 degrees. And if that number bothers you, imagine it being 89.99 degrees. The angle on the other side of the interface is a very special angle called the critical angle. And if we think of this configuration, there's really no way that we can get an angle any larger than the critical angle on the other side. As theta1 becomes smaller, theta2 will also become smaller. So there's that cone of angles that's actually impossible to achieve on the transmitted side. Now, even more interesting, if we think about this configuration, however, let's have the wave incident from the bottom instead of from the top. And let's think about what happens. If the wave is incident from the bottom, but at an angle larger than that critical angle, remember that's in this cone of angles, that there was no possibility in the first region to create in the second region. So when that is the case, we get something called total internal reflection, and that incoming wave will totally reflect from an interface. And so we conclude that for total internal reflection to occur, the wave has to be in the high refractive index material, and it has to have an angle of incidence greater than the critical angle. And when that happens, none of the wave will transmit through the interface, it will only reflect. So now, rather than have one interface, let's have a slab of material. We will call this our slab waveguide, and it will have refractive index N2. And let's surround that by two different media that have a lower refractive index than that middle layer. That means we could get total internal reflection on either side of that slab. And this really is what causes waveguiding. The wave is at a shallow enough angle or large enough angle such that we get total internal reflection from either side. Well, waveguiding is a little bit more complicated, and let's talk about that. If we trace the path of a wave, that's the red line here. We're going to trace the path of a wave. And if we look at two common points, and it's essentially the same point because this repeats, we have to look at the phase of the wave at those 2 points. And if that is not an integer multiple of 2 pi, it turns out that wave inside the slab waveguide will interfere with itself and leak out of the waveguide. So it's only under that special circumstance where the phase from that common point to common point is an integer multiple of 2 pi that we get a guided mode. And this is really the origin of having only a small set of modes that could be supported by the waveguide given a fixed frequency. So we have discrete modes, and this is the hand-waving sort of qualitative argument of why we have discrete modes in a waveguide. Now, the ray tracing picture is great for explaining things in a simple manner, but really these slab waveguides have to be simulated and analyzed rigorously from Maxwell's equations. Maxwell's equations are, of course, the equations that describe classical electromagnetics. And when we do that, out comes pictures of these discrete modes. And going from right to left, we see the first order mode, the second order mode, third order mode, and so on. And at some point, there won't be any higher order modes for a certain frequency. And those modes are what's called cut off. And they decay as they propagate or leak out of the waveguide. They're not guided modes. And so for this particular case, I don't know how many guided modes there are. I know that I'm only showing 5. So it may be that there are only 5, or I just chose to only show 5. So this is an example of what we would get from our finite difference analysis. And so this would be and will be a rigorous solution to Maxwell's equations. Just to generalize the concept of a waveguide real quick, right now we are analyzing slab waveguides. And that's where we have this infinite slab that's sandwiched between two different types of materials. And the wave guiding or the confinement is only in the vertical direction, not in the horizontal direction. The wave is free to spread out in that direction. And the reason we're analyzing a slab waveguide is this is a very good thing that can be analyzed in just one dimension. Probably more useful are what are called channel waveguides. And these act much more like pipes where they have confinement along two different directions. And in both these cases, the actual mode that's propagating is in and out of the screen. So channel waveguides are really inherently a two-dimensional analysis, and that would have to wait until we get to two-dimensional analysis. So we've only, at this point, learned a one-dimensional finite difference method. So that's why we're analyzing slab waveguides. And slab waveguides are hugely useful. In research in my EM lab, we've simulated slab waveguides on at least 4 different projects. And so the one-dimensional simulations are actually very useful. We need to understand the mathematical form of the solution and maybe what it looks like physically. So on the left here, I am showing a slab waveguide, and we will let our wave, the guided mode, propagate in the z direction. So that's what I'm showing by the red wavy thing. That's our picture of a wave. So in the z direction, the wave accumulates phase, and we will describe that oscillation and accumulation of phase with a complex exponential, e to the minus j beta z. Now in the x direction, the mode has a certain intensity profile or amplitude profile in that cross section, and that's what we're drawing when we draw this. And so we'll call that ax. It's only a function of x. And in fact, if we look at the y direction, nothing is changing. Our slab is uniform in that direction. Our electromagnetic mode is uniform in that direction. And it will turn out later on, this helps us simplify the mathematics considerably. But the overall electric field has that amplitude profile, which is only a function of x, multiplying this exponential, which describes the oscillations or the accumulation of phase in the z direction. That is only a function of z. Nothing here is a function of y. Okay, so we're armed with some basic electromagnetic concepts that will hopefully let us understand the mathematics that we're about to dive into. So in the next section here, the formulation, we will start with Maxwell's equations, and we will work with them and whittle them down till we get a single final equation that we want to solve with the finite difference method. So let's dive right into it. Here we go. So formulation, we will start with Maxwell's equations that we're showing on the left. And there's actually 4 of Maxwell's equations and 2 others called the constitutive relations. And so we've combined these, and we have 2 equations left that we will use for this analysis. And these are commonly called Maxwell's curl equations. So these are vector differential equations, and there's 2 of them, and they're coupled. And somehow we will manipulate this. We will then use the finite difference method to cast that system of equations into an eigenvalue problem. Remember when we talked about this earlier in the semester, we tend to get 2 things in numerical analysis. We either get the ax equals b, and those problems arise when there's a source and only one answer. Eigenvalues arise when there's no source and we're really just asking a question of what could happen. And in this case, our question is, what do these guided modes look like? So we handed a picture of our slab and we say, what kind of wave goes in this direction? And out comes the answer. And it has pictures of the modes and their propagation constants. And that's what we're after. So we start with these governing equations, and we end up with a matrix equation. So when we do this formulation, there's going to be equations all over the place. Don't get yourself into a mentality where, oh my gosh, how is my code going to do all this? Well, your code doesn't. That's why we're doing this on paper. The implementation will be very simple. So don't mistake formulation for implementation. Formulation, we're after that one matrix equation and how we build it. Okay, here we go. So we start with Maxwell's curl equations. And for those of you that are not real familiar with vector calculus, this little upside down triangle is called the del operator, and the x is a cross product. So when we do an operation del cross a vector, we're calculating what's called the curl. And in this first equation that I highlighted, we're asking the question or trying to quantify the tendency of the electric field E to circulate about some point. And curl gives us another vector, and the vector is pointing down the center or the axis of rotation of that circulation. So the first equation says the curl of the electric field, or if the electric field is circulating, we're going to have a magnetic field H at the center of that circulation. And this term mu is the permeability, it's a material property. That's really the proportionality constant. And the other equation is almost the exact same thing. If we have a circulating H field, there will be an electric field at the center of that circulation. And the permittivity, the epsilon variable here, is the proportionality constant. So in Cartesian coordinates, I wrote on the bottom the vector curl operation. I don't want to spend a lot of time talking about that here. I do think it's important for understanding the electromagnetics, and I'd recommend pausing the video here, maybe going to Wiki or the internet and searching about vector curl to learn a little bit more about that. But we're going to move on. So we look at our first equation, del cross E equals minus j omega mu h. That is a vector equation. So the electric field E and the magnetic field H are both vectors. So we can expand this into Cartesian coordinates. And on the left, we've not only expanded E, we've expanded that curl operation according to the expansion we showed on the previous slide. So this is the same equation, just expanded into the vector coordinates. At this point, we will look at the x component on the left, and we will set that equal to the x component on the right, and arrive at this equation. The other two equations on this slide are arrived by setting the y component on the left equal to the y component on the right, the z component on the left equal to the z component on the right. So our single vector differential equation has now become a set of three scalar differential equations that are all coupled. They're not independent equations. So we started off with two very simple curl equations, and we expanded one of them into a set of three. Turns out we can expand the other one into a very similar set of three equations. So this is very common in electromagnetic analysis. Start off with the curl equations, expand both, and we end up with a set of six coupled partial differential equations. So far, we're still in three dimensions. We have x, y, and z. And I suggested before we will use the geometry of the slab waveguide to help us simplify the math. So looking at our slab waveguide, let's think about x, y, and z. Well, in the x direction, the material properties are changing. The mode itself, the profile of the modes are varying in the x direction. So things are changing along x. And there's nothing we can do with it. We have to retain x. We have to retain the derivatives in x. So we don't touch x. Y. In the y direction, the slab waveguide itself is perfectly uniform. Nothing changes in the y direction. As long as we let the mode propagate only in the z direction, there's nothing about the modes that changes in the y direction. So if nothing is changing in the y direction, then any derivative in the y direction just has to be zero. And so this simplifies the math. We look for y derivatives in that set of six equations that we had, and we just cross them off. And we'll get to that. Now in the z direction, the slab waveguide is uniform. So maybe we're tempted to say, well, if we take any derivatives in the z direction, that should be zero. And that's not quite true, because the wave accumulates phase in the z direction. So the derivative in the z direction of the wave is not zero. Now it'll turn out it's just a little constant minus j beta, and we'll get into why that is in a few slides. But the point is, we can simplify our system of six equations down using what we discussed on this slide. Okay, so here's our set of six differential equations, and now we want to apply the fact that any derivative in the y direction has to be zero. So we will find all of the y derivatives in our set of six equations and cross them out. And we end up with a new set of equations that do not contain any y derivatives. So we're already a little bit simpler. This is the same set of six equations on the previous slide, but I've color-coded them in a special way. And if we were to stare at this long enough, what we would realize is that all the equations in blue do not contain any of the terms that appear in the red equations. And the red equations do not contain any terms from the blue equations. So by setting that y derivative to 0, our set of 6 coupled partial differential equations have in fact split into 2 independent sets of 3 equations. And so in the electromagnetic jargon, we would say we actually have 2 modes, 2 types of modes that are supported by a slab waveguide. If we group all of the blue equations together, we'll call that the first type of mode, or we'll call it the EY mode. And the reason we call it that will come up later, but the short answer is it'll turn out we can combine all these equations into just a single differential equation containing only EY. So we call that the EY mode, but that hasn't happened yet. Then if we group all the red equations together, we'll call that the HY mode. And really, to know everything about the slab waveguide, we have to simulate both of these, and they lead to slightly different codes. But because of how we've learned the finite difference method, implementing one and then modifying your code to implement the other is essentially trivial. So in this lecture, we will proceed only with the EY mode because the HY mode is essentially exactly the same. And once you see how we do the E mode, how we do the H mode is trivial. Now let's think about the Z derivative, because the device was uniform in the Z direction, but the wave was accumulating phase. So what we do with the Z derivative wasn't exactly clear. So let's go back to the equation for our guided mode. The overall electric field we will write as an amplitude term, which is only a function of x, and then this phase accumulating term that is only a function of z, because we're letting our mode propagate in only the z direction. So let's ask the question, what happens if we take a derivative of the electric field? So we replace the electric field with our expression a times e to the minus j beta z. When we calculate the derivative, we use the product rule. And then over on the right here, we need the derivative of a. Well, a is not a function of z, so this whole term just drops off. And we end up here. Then we recognize that we have an a times e to the minus j beta z. That was just the original electric field. So we can write it with the original electric field. And now we look, the derivative of the E field is minus j beta times the E field. So we can come to a rather profound conclusion. We can just replace our partial derivative with respect to Z with minus j beta. Remember, beta was the propagation constant. That's the number that tells us how quickly the mode accumulates phase as it propagates. So we will go into Maxwell's equations. We will pull out all the Z derivatives and put in minus j beta. So here we are, and I've highlighted the Z derivatives here in blue, and we want to replace those with minus j beta. So now we're here. Notice something else in this equation that has changed. What was the partial derivative in the first equation with respect to x has become an ordinary derivative. And mathematically, that's very important. The reason that has happened is because there's no longer y or z. X is the only independent variable left, and so that let us write our partial derivatives as ordinary derivatives. Now in computation, we always want to normalize everything, and that goes back to when we talked about errors. If you have two numbers, and one is on the order of 1, and the other is on the order of 10 to the minus 3, and we're adding and subtracting those, we're losing digits of precision every time. We really would like every number in our method to be as close to 1 as possible. Now in electromagnetics, our dimensions could be micrometers or meters or even kilometers. And so we don't want this kind of range of numbers in our model. So what is normally done is we take our dimension x and divide by the wavelength. So now everything is in terms of wavelengths. And our slab waveguides, the dimensions of that are almost always on the same order as the wavelength. So this x tilde now will be a number like 0.5 instead of being 10 to the minus 6 if the physical device is in microns. So we want to use these normalized coordinates in our model that we're developing. Now in Maxwell's equations, we have this parameter k naught. It's called the free space wave number. It's 2 pi divided by the free space wavelength. And it will turn out to be very convenient, rather than just divide by wavelength, although we could do that, to multiply our coordinate by k naught. We're still dividing by wavelength, but we also have this 2 pi in here. The 2 pi doesn't do anything for us. It's just the fact that the 2 pi over lambda is a k naught, and it'll turn out we're going to have this k naught just appear on its own in Maxwell's equations, and if we normalize it this way, then the k naught kind of isolates to one place, and it'll simplify the math. Okay, so let's look at one of the equations that we had in our set of 3 for this E mode, and let's normalize the x coordinate. So notice the derivative here. We had an ordinary x. Now we have an x tilde, but we need to divide this x tilde by k naught. Now, since this x tilde is in the denominator, we're multiplying by k naught. Now what we want to do is divide both sides of this equation by k naught. So that means we have our derivative back again. We have a beta over k naught, and then we also have our epsilon over k naught. Looks like we've complicated things, but let's keep going because it will simplify down as I promised. Remember when we were first talking about slab waveguides, we had the free space wave number multiplying the effective refractive index, and that equaled our propagation constant. So if we divide beta by k naught, we just get our effective refractive index, and that will tell us essentially how quickly that mode propagates. Remember, refractive index is the factor by which a wave slows down inside of a medium. So k naught is disappearing on us. That's very useful. Now, I can play some games with the parameters here, and I don't expect you to follow the electromagnetic theory here, but we expand our epsilon as a free space epsilon and a relative epsilon, sometimes called the dielectric constant. We expand our k naught as omega times the square root of the free space permeability and free space permittivity, and we cancel a bunch of terms, and we end up over here. Okay, so if we apply the same normalization we just did to all 3 of equations for this E mode, we end up here. Now, at optical frequencies, and we want to do an optical analysis here, and in fact, most materials do not have a permeability, and so we would say that the relative permeability is just 1. And that helps us simplify. So everywhere we see a mu r, we'll just replace that with 1, and we'll end up here. So we're ignoring permeability, and for an optical analysis, that is perfectly valid. Even at microwave frequencies, there's essentially very negligible permeability. It's really only at lower frequencies that becomes significant. And it's not too big of a deal to leave permeability in here. I'm just eliminating it now to make this as simple as possible to illustrate the finite difference method. Okay, so on the left here, we have our 3 equations that have now been normalized. So we have the x tilde, and we manipulated some of the parameters to simplify our constants. These second 2 equations are solved for hx and hz. So we now have the 2 magnetic field components written in terms of the electric field components. And then we will take these expressions and substitute them into the first equation. So when we do that, here's our equation with the magnetic fields. We do our substitution, and we simplify down to this. Wow, look how simple that is. And this was really the reason that we did the normalizations and that we did our normalization in terms of the k naught, because it turns out that would drop out of the equation. And of course, there's a lot of other electromagnetic theory that would have given us clues to this, but that's not really so important for this computational class. If I was teaching an electromagnetics class, we would go a bit more into that. But we did all this so that we'd whittle this down to a single differential equation that's very, very simple, and we are there now. So we'll rearrange the order of the terms, and we'll write our differential equation this way. Notice this is an eigenvalue problem, and we're asking a question. What on earth could happen in the slab waveguide? And the solutions to this give us the modes. So on the left-hand side, I'm going to factor out EY, and on the right, not really do anything. But what I will also do, if anything is a function of x, I will explicitly write it as a function of x, just to remind us that that is a function of x. When I'm working by myself on paper, I usually don't write that. But if you're new to this, I think it's easy to lose track of exactly what is a function of x and what is not. So I've written that explicitly here. So from a formulation perspective, I would say we've arrived at our final governing equation. And the only thing really left to do now is to take this into matrix form and form the matrix eigenvalue problem. So armed with how we do our finite differences, where we write our differential equation and we go term by term and convert everything either to a scalar constant, a square matrix, or a column vector. Now in this case, we only have our unknown. There's no source or excitation, so this EY is the only thing that is stored in a column vector. So in these column vectors will be the electric field at each point. And if we were to plot it, we would see pictures of our modes. Well, the second order derivative becomes a square matrix, calculating a second order derivative across the grid. And this refractive index is doing a point-by-point multiplication. So that becomes a diagonal square matrix where the refractive indices in the cross-section of our slab waveguide are stored along the diagonal of a matrix. And of course, our eigenvalue is stored just as a constant. But we now have a matrix eigenvalue problem. Sometimes I like to write this in terms of the permittivity instead of refractive index. Solving optical problems, people like to talk about refractive index. Numerically, when we're solving Maxwell's equations, the permittivity is a little bit more fundamental. So we have two matrix equations. Both will give us the same answers. Both are equally valid to use. So I'm just showing them both here. So we now have our final matrix equation. That is the formulation. At this point, we need to discuss how to solve it and how to interpret the solution. Oh, I'll mention one more thing, sorry. On the left, we will calculate this as one square matrix, and that is our eigenmatrix. And of course, this term over here is our eigenvalue. And I'll remind you one thing, another way to think of an eigenvalue problem. Pretend we have a guess for our electric field and the cross-section of the waveguide. If we can pre-multiply these square matrices, so we're doing a bunch of math on that, and if we get the same exact answer back after doing all that math, just scaled by a constant, then that was a valid solution to the eigenvalue problem. Okay, let's go on and talk about the solution, how to solve this and how to interpret the solution. Now that we have the equation we want to solve, let's talk about what that solution looks like. After that, we'll talk about how to actually do this analysis in MATLAB. So we have this matrix equation in the form of an eigenvalue problem that we need to solve. When we solve this, we calculate a big square matrix V, and the columns of that matrix are the eigenvectors. We get another square matrix we're calling lambda, and this is a diagonal matrix, so it's all zeros except numbers going down the diagonal. And the eigenvalue matrix are containing the eigenvalues, the effective refractive indices squared. Now, eigenvectors and eigenvalues come in pairs, as you'll see. So looking at V, and we look at the columns, we see different modes. And if we have nx number of points on our grid, our matrices will be nx by nx, and we'll be calculating nx modes. So each of the columns are the modes. We'd look at this first one. If we were to grab this array of numbers and plot it, we would see a picture of one of the modes in our slab waveguide. This D matrix is also a square matrix, but it's a diagonal matrix, all zeros except the effective refractive indices, I should say effective refractive indices squared, running down the diagonal. Now, why are the effective refractive indices squared inside of D? Because that's how we formulated our eigenvalue problem. That was the effective refractive index squared. Now, I mentioned that the eigenvectors and eigenvalues come in pairs. This first eigenvector is paired with the first eigenvalue. The second eigenvector is paired with the second eigenvalue, and so on. We never want to mix these up. Each of these modes has its own effective refractive index, and so if we mixed it up, we would be getting something wrong. I guess in my mind, I am picturing the eigenvector matrix a little bit more like this. And so I think this more clearly conveys that the columns really are showing pictures of the modes. And so if we were to overlay that on top of our original slab waveguide, it's even more obvious that we're looking at the modes of the waveguide. So that's really it for interpreting the solution. The next thing for us to talk about is implementing this analysis from beginning to end in MATLAB. So in this section, we will be implementing it in MATLAB, and you will see every single line of MATLAB code. We may not discuss all of them, but we will discuss the key ones. So the finite difference analysis of a slab waveguide, we are going to perform in 6 steps. Like most of the codes we write, the first thing we'll do is we'll initialize MATLAB, clear the command window, close all the figure windows, clear memory, that sort of thing. Then we have our dashboard. This is where all of the hard-coded numbers go. We don't do any work inside of the dashboard. This is just our controls for controlling the rest of the program. And the rest of the program will not have any hard-coded numbers. It's all controlled through this dashboard. The first real task after defining everything about our problem, the materials, dimensions, number of points on the grid, and all that sort of stuff, the first thing to do is actually calculate the grid. So this is the size of the grid, number of points on the grid, the spacing on the grid, that sort of thing. Once we have that, we're now ready to build our device on the grid. In this case, our device is the slab waveguide. And our goal here is to assign values of permittivity or refractive index to every point on the grid so that if we plotted that, we would see a picture of our slab waveguide. Once we have that, we're now ready to perform the finite difference analysis. And what you'll see is this is actually a pretty short section of code. When that's done, our finite difference analysis is done, and we're ready to visualize the results. So let's dive in and look at the code. So what we can see is up front, we have our initialization where we're closing all the figure windows, clearing the command window, clearing memory, and we enter our dashboard. The first thing we'll give it is our free space wavelength. I'm just calling this 1, and there's no units here. That could be 1 meter, 1 nanometer, 1 anything. And the reason we're allowed to do that is we will put all of the dimensions of our waveguide relative to a wavelength. So we'll be expressing A and B in terms of wavelengths. And in electromagnetics, things are scalable, so this works. The next thing we'll define is our slab parameters. We need the refractive index of the core, which we're setting to 2.0, and then the refractive index in the surrounding regions, the cladding, which we've set to 1.0 or air. And A is the core, and we're setting this to 3 wavelengths wide. Not expecting you to have deep knowledge of waveguide theory, but that's a pretty wide waveguide, and this will be multi-moded and support multiple modes. So that's it for the slab. B is not really needed for the slab because those regions with refractive index N2 really are intended to extend out to infinity. Now clearly we can't do that in our model, and so we have to choose some distance B that's large enough. to make this work. And here we're trying five wavelengths. Not five different wavelengths, I misspoke there. 5 wavelengths. And what we're looking for is to see the mode in the vicinity of the core, and then it drops and decays to 0 and stays 0 out to when it hits the edges. And that's the sign of it being a guided mode. The resolution we're setting to a 20th of a wavelength. So that number 20 there is something that we can play with. And what we'll want to do is make that 20 larger and larger. So we'll be getting finer and finer resolution. The simulations will take longer. But what we'll see as we crank that number up, that our answers at some point stop changing very much. And we call the algorithm converged at that point. And so that's a number we'll play with. And the very last thing on our dashboard is the number of modes to calculate. So we're only calculating the first 5 here, but we can change that just by setting that to a different number. Okay, on to the next step. This is the stage where we want to build the device on our grid. And the first thing is to set up the grid. And the first number I like to calculate is SX. This will be the physical size of the grid. So it contains the core, which is of size A, and 2 different cladding regions, if you will, the top and the bottom, both of size B. So SX is just A plus 2 different Bs. Then the number of points on our grid is the physical size of the grid divided by the grid resolution. But an issue that can come up is that number can be a fraction. It won't necessarily come out to be an integer, so I am rounding up with the ceiling command in MATLAB. However, once I've rounded, the physical size of the grid is now slightly different, and I don't ever use SX again in this code, but I just recalculated it just to make sure that everything's consistent. After that, I calculate a vector that tells me the position of each point on the grid, and I'm centering it, so position 0 is in the middle of the core. At this point, I want to start building values into this array N, which will contain the refractive index at each point. So to center the core, the first thing I'll do is calculate how many cells wide the core is. That's this little nx. So it's A divided by dx, and I round that just so I don't get any fractional numbers. And then I calculate an nx1 and nx2. And these will be the start and stop indices of where to place the core. And I'm calculating these in a way that would center them in the grid. Once I have those, we're ready to start. So I'll initialize this array N to all ones. So that means I'm setting it to air. And then I go ahead and I fill in the top part of the waveguide, the core, and then the bottom part of the waveguide. And you can see how I'm using those array indices nx1 and nx2 to do that. You'll also see we're filling in the middle from nx1 to nx2 with values of n1 and the rest with values of n2. So at this point, we've calculated our grid and we've built the waveguide. So we're ready to perform the finite difference analysis. And this code you see, that's it. That's all there is to our finite difference analysis. The first thing I do is calculate the free space wave number, 2 pi over lambda 0. And the reason we need that is because we have a normalized grid, if you remember doing that in our formulation. Now what we're after first is to build this matrix A, which is our second order derivative matrix plus a diagonal matrix with refractive index squared. So under this heading build dx2, I'm building this big square matrix that would calculate a second order derivative. Now, of course, we're not using it to actually calculate the second order derivative. We're using it to build the bigger matrix A. So the first thing I do is I set it all to zeros and call it a sparse matrix. Then I go ahead and I insert the 3 main diagonals that you see. You see 1s and -2s and another diagonal of 1s. And so these 3 lines of code is what's doing that. And then the very last thing is I divide by the grid resolution, but the normalized grid resolution. So it's k times dx, that quantity squared. So at that point, we have our derivative matrix for second order derivatives. Well, we already have a one-dimensional array N containing the refractive index at each point. So I reshape that first by column vector, declare it to be sparse, then make it a diagonal in a matrix. At that point, we have this diagonal matrix N. Now we're ready to build the matrix A, our eigenmatrix, if you will. So it's the dx squared plus n squared. We've built our matrix A. Now we're ready to solve the problem. So I'm calling Eig. This is not the sparse Eig, and I'm calling that because that's a little bit faster than the sparse version of Eig, which is called Eigs. It ends with an S for sparse, and it doesn't like to see sparse matrices, so I declare A to be full. And I'm asking it for the eigenvector matrix and the eigenvalue matrix. Now remember, the eigenvalues here are refractive index squared, the effective refractive index squared. So the first thing I like to do is extract the diagonal and then take the square root of that. So now I have a one-dimensional array of the effective refractive indices. Sometimes I also might put a real operation outside of the square root, because every once in a while some very small imaginary numbers can pop up, like 10 to the minus 16 order of magnitude, and that would clean them up. I didn't have that problem here, so it's not there. So that's it. That is the entire finite difference part of this code. There was some work setting up to do the finite difference, and then the next we want to display our results. So this is the very last part. We're displaying the results. A few of the graphic techniques that I've done here, notice the blue lines have a slight white glow to them, and that makes it stand out on a contrasting background. And I do that simply by plotting the line twice, once with a thick white line and next with a thinner blue line. So in this graphic, I am showing the dimensions for the x-axis on the left. I'm labeling which mode number we're displaying. Of course, we're displaying the mode, and then also giving the effective refractive index for each mode. And of course, we could play with this in large font sizes and do other things, but I think that's a pretty good output. And we've done graphics calls and things in the past, so I'm really not going to go through this here. So that's it. That is slab analysis using finite difference method.